All right, as mentioned today, we will not take attendance, but we'll resume that maybe next week. And I'll still give you guys maybe 1 or 2 breaks in between, so just get a little bit fresher, before the next topic. All right, so now we start a brand new lecture by model checking. So this is gonna last us for definitely a few weeks, maybe definitely beyond reading week. And after this, we'll also need to talk about whole triple, like a program verification. That's something we'll get into in the last part. But this will be definitely the main part for this course about model checking, okay? But for today, we still need to start a little bit about clarifying some concept and some little introduction. That one shouldn't take too long. We'll do that first and take a little break, and then we definitely will see LTL today. But today, the LTL will still be on the lighter part. Let's clarify all the syntax first, and then before we talk about the meaning for LTL. That will definitely last us for long, for a tricky example. We'll get there. Oh, before that, that's about the plan for today. Sorry, just before that, there's one thing important to let you guys know for your information, okay? 2 things, actually. For your lab number 1, part 2, I mentioned that already, but the new information is this, about some flexible TA hours. I'll show to you what I mean by this. If you go to the E-class for the course, and then you will see that under TA's contact over here, if you click on that, you will see this TA email over here. So this Echo used to be our student. She's now doing like a PhD in Waterloo, but she's working for us as a TA. She knows very well about the syntax in TLA+. So if you got any trouble with your lab, you want somebody to maybe troubleshoot together with you, this is how it works. I believe she works also quite late in the evening. So you can send her email whenever you want to get some help, and then she'll try to respond back to you. And then you guys can sort out either things over email, or she can also Zoom together with you. But she works remotely, not in person. Okay? So take advantage of this resource over here. In addition to my office hour, it will still be normal, but this will be something for you guys. Okay? Flexible, anytime you like. But of course, if she doesn't respond, then you will have to wait, or just get back to me. All right, that's the first thing I want to mention to you. And the second thing is, over here, you guys asked me about which textbook I'm gonna use to base on my slides. So there you go. For both the model checking, for sure, a large part, and a little bit about program verification as well. So this is a textbook. You guys can either find some online resources, or maybe just check out the library, or if you want to purchase. It's a very tiny book, but a little bit pricey. Published by Cambridge. But anyway, nice book, but I'm gonna follow that very closely. And sometimes I might use maybe other example from other textbook. Anyway, I'll leave the choice to you for your reference. Alrighty, let's now move on to introduction to model checking. Many of the stuff have been already mentioned back in the introduction, so I'll just mention them as a bullet points. There will be many things you can look back to the introductory lecture. But it's good to have a little bit more narrowed down, more targeted introduction for just model checking versus theorem proving. Safety critical system, know the definition, versus mission critical. An example would be, for example, shutdown system that involves lives. And mission critical system, one thing we didn't quite mention before, mass-produced computer chips. That's definitely mission critical, right? If you did it wrong, you're gonna lose lots of money. And I'm gonna quote one story for you by in Pentium. So that's an old story. I'll read some passages together with you. That's very specific about model checking. Okay, and then formal verification. We want to formally verify the correctness to prevent loss of fortune or even lives, right? That's something we talk about in the introduction. What would be the ingredients or components for formal verification? 3 things. We got system, and try to relate back to your lab number 1. What kind of system are we building? We use a procedure, we use a loop to simulate event selection, right? That's a system specification. And the language we're using will be Pascal, which is translated into TLA+. And that's abstraction, because it's not exactly coding. There are certain details that's abstracted away. And property, so far we only talk about invariant property, and also deadlock freedom. But that one is also encoded as invariant. That's also what you learn. But we're gonna see some syntax of temporal property today. Not really get into the deep meaning of them, but at least we'll see some syntax. Verification. It would be a systematic method here. And think about the systematic method in this course, model checking versus theorem proving back in 3342, right? So these are the components. Any formal verification you want to do, always consider these three components. What are they going to be like? All right, and then, yeah, that's also, remember some design, some chart I mentioned. The earlier you catch the bug, the more cost you can save, right? That's also, I think that was in the lecture that was missing for its recording anyway. So you can refer back to the slides. The earlier, the better. Good. All right, so the first slide here should be nothing surprising to you, but it's now really narrowed down to formal verification. And one example would be, so this is a very old bug in the last century, okay? But it's actually worth knowing about. It's called the Pentium FDIV bug, okay? You can find some information in the Wikipedia, or you might even be able to search for some news article on that. But I just got some relevant passages from the Wikipedia. So I'm going to read them together with you, just with some highlights, so you can have some knowledge about it. Let's take a look. Okay, so again, that's the link for the Wikipedia. Okay, let's read this one first. So this bug over here is a hardware bug, not software, hardware, okay, in the chips. And it has to do with floating point number, okay? And then that's in the early Pentium processors. Because of the bug, the processor somehow returned incorrect binary floating point result. You can kind of imagine what it might be, right? In some very boundary cases that the engineers haven't thought about, right? And somehow, of course, when you do some division. So when you do some division, there will be some lookup table for you to get a result. And somehow you return the incorrect result in some boundary cases. It does not happen always, but only in the edge cases. That doesn't happen often, right? That's kind of the context, okay? It has to do with floating point. In 1994, right? I guess most of you haven't been born yet, right? At that point, Intel recalled the defective processors. And they claim that they lost $475 million. That's what they have lost. And of course, what's the lesson learned from in Pentium? What happened is the bug in the subsequent recall, okay, increased in the use of formal verification. That's what they claim. And then, especially, you want to look at, they got something called word-level model checking. You can think about this is more about model checking at a machine instruction level. That's what you can understand. That's about checking at the machine instruction level. Okay, and also, let's see over here, there's another one. Okay, so in the development of their later processor, they also try to use theorem proving. Okay, this part's interesting. I didn't really follow through the detailed story. Remember what I mentioned before, model checking inherently should really deal with integers, like a TLA plus. But this one here has to do with floating point. So my imagination is, when they try to do the formal verification, they might simply got a combination of maybe model checking and theorem proving. But just remember, when you want to apply formal verification, you don't necessarily have to go to one way, but not the other. You can definitely combine both. That's the main thing. And then they definitely finding a number of bugs that could have been led to similar recall incident. So they definitely find formal verification being valuable, right? So that's one example that they use model checking. Of course, they didn't reveal the exact details, but that's a story. Right, that one just for your information. So model checking and combined with theorem proving can really be very promising, okay, for anything you want to verify. Okay, what about classification of verification method? This slide will be important. Remember that symbol I did the other day, but I'm going to clarify that. First of all, how do you classify a verification method? There are several criteria. One would be, how much can you automate the process? This is also important to know, to compare the two courses. It can be either completely automatic, interactive, or manual. In this course, it's completely automatic because we're doing model checking. All you got to do is click on the button there and see if there's any success, green light, or error trace. these are the only two outcomes. Of course, the third one. If somehow you run into state explosion problem, it will never terminate. Will just terminate with some out-of-memory error. Okay, it's summarized in another slide. Automatic will be the case for now. And interactive or manual are usually the phenomenon for theorem proving. So that means you can try to run the auto-prover in rodent. It may prove it. In that case, you're lucky. Otherwise, you have to intervene with the proof process. In that case, you got to do lots of mouse click and try to apply different inference rule and etc. Okay, so that's really what I mean here. It's good to know. And if you ever refer to the textbook I just mentioned to you, it's actually chapter number 3 about model checking. They talk about model-based versus proof-based. However, I think the model over here could be confusing because, confusing in our context. Remember in the introduction lecture, we said both 3342 and 4315, we talk about model-based developments. So the model we are talking about here is a little bit different from their model. So I would say avoid this word, okay? So I would rather say it's check-based versus proof-based. It'll be much more straightforward for you guys, okay? Just note that point. All right, so let's talk about these comparison. Okay, so let's see what we can do to compare them. Okay, so we got basically proof-based and check-based. And I'll try to maybe link back some example you did earlier last year, just to brush out your mind very quickly. Let's go with the proof-based. That's what you did before. It's good to recall very briefly. Okay. The proof-based is summarized as a sequence rule, something like this. Okay? If you remember that dash, right? That V dash. Okay, let me just make sure I write it right. Okay? So something like this. So this is Greek character gamma, and then V dash, and then some formula phi. Okay? What does that mean? Okay, let's understand in the intuitive sense, and I'll show you just one example. This means derivable from left to right using the relevance inference rule. All right, let me show you one example right away, and then I will go a little bit deeper into this, and then that'll be it for the recall. All right, let me bring it up over here. Let's go back to where we were a year ago, okay, 3342. I want to show you very quickly. I wouldn't go into details. That's not the point. I think somewhere I got some proofs document somewhere. Let me find it quickly. Could be, okay, sorry. Proofs. There we go. Okay. Okay, I want you to look at this one here. Might seem familiar, right? Okay, what should you pay attention to now? Okay, so here, first of all, you can see the V dash. Okay, you see this guy over here. You think about this is the left-hand side. This is really the gamma. And what we really want to derive is some property over here. So what's really important to note, the way we describe the system over here in this sequence calculus itself is a predicate, is a formula. The property itself is also a formula. We want to make sure the system formula is derivable to the property formula. Okay, let me write it down. Okay. So this one here is the system formula. Okay, based on the before-after predicates of actions, after predicates of actions, and things like guards of the events, and also invariant, and etc. Right? Everything can be combined together into a very large predicate, right? That'll be the antecedents or assumption we can make. And we want to say, based on this, we can apply a series of inference rule, and then finally get to the property we want to prove. That's basically what we're doing. So this one here really summarizes what we were doing in this whole course. And this one here is the property formula. Okay. And you may also want to think about this as so-called a deduction. Right? You want to deduce from here back to here by using the relevant inference rule. Right? Maybe you have heard about this term in your math course. All right, guys, don't be terrified. We are not going to touch this approach, this course, right? I just want to remind you, okay? If people ask you about what did you learn in 3342, quote this formula to them. That's basically what you did in the high level. If they want more details, you can ask them to go to my website. That's okay. They can learn about it, all right? You don't need to bother, all right? Okay, that's about the proof-based. That's all you need to know. Let me go back to the slides. And, one thing that's very important. In theory, very quickly. That's why if you talk about this particular thing, okay, it's important to know this is an undecidable problem. In general, given some arbitrary formula and given another arbitrary formula over here, does there exist a sequence of inference rule that can derive from one to another? This is, in general, a hard problem. Okay, that is why this cannot necessarily be automatically automated. So you got somehow you also need some manual intervention. Yes.
Is that like semi-manual?
Yes, exactly. Yes. So, that's also important. So if also very important thing you should know. That's exactly the right point. Let me go a little bit deeper, just for your information. Even if there exists a sequence of inference rule that are application rules application between and, okay? So even if there, let me finish this and I'll take a question. Yeah, even if in theory, there's indeed some connection between these two, okay? Like a Faraday model tells you that there does exist, really. However, can the tool really find it? That's another story. There's no guarantee in general the tool can really find it, even though there does exist. A theorem prover cannot get a theorem prover cannot find it in general. A theorem prover cannot always find it, because as long think about to really get to that from here to here, you have to take different branches, different decision for each point. If you take the wrong one, of course, it's going to lead you to some dead end. So that's why manual intervention will be necessary in that case to really help. All right. Yes, question.
I was curious, is this related to the three-stat problem?
The
Three-stat or like three-stat. It's basically like satisfiability of
the SAT problem, yes, yes. Yeah. Undecidable, yes. Very good. Okay, guys, just a high-level information for you. And let's now go to the more relevant, which is the model. The model checking. Okay, check-based. And for check-based, let me see the symbols I used. Okay, M and fine. Okay, and let's now put them side by side. Okay. Let's say we got. All right. Okay. For the check-based, this will be the formula to look at. M. And then this is what Chidalu asked me last time. And now we're going to explain it more precisely. And also phi. Okay? So these are the two. Okay? This part over here is a system model also, but it's not necessarily just predicates. We're not doing any proving. Okay? this will be the system description. And usually formulated as a it's called label transition system, which we're going to talk about before we when we talk about the LTL. Okay, label transition system, like a state graph. Label transition system. And I'm pretty sure you guys have already seen this in your lab number 1, part 2, right? You can actually generate this LTS for your Pascal model, which is based on the TLA plus translation. Okay, usually formulated as an LTS. You can think about this to be more relevant to 2011. It's a graph, basically. Okay, a graph. And this symbol over here, to put in the intuitive term, you can think about it's more like a satisfies. Whether or not the model we're building with certain restriction, remember how we create a model, right, in TLA plus. That one there satisfies this particular formula, which tells you the property, which can be either predicate property, or it could be temporal property. And this one here could be, for example, invariance, or it can be temporal property. And of course, in this course, we'll first look at LTL, and then we'll look at CTL. We'll look at both. Okay? And why are these two approaches different? Okay? Remember we said before, this approach is completely automated. In the sense that build a graph, and then traverse the graph. Traverse the graph to check the property. And once you got this kind of conceptual understanding in your mind, you can easily tell what are the possible 3 outcomes. If I try to build a graph, if the graph itself is already infinite or too large, it will already take too much memory to build a graph, right? Or the graph is simply too large, it takes too much time to traverse entirely. That'll be the state explosion problem. When the graph itself is too large, you got too many states to consider. Eh? Oh, I want to say the side notes. I think a good news for you guys. Remember we talked about the Sudoku example, right? On Tuesday. I spoke to the TA, I just mentioned, we managed to somehow create a simplified version of that. And we'll do the following. I'll choose maybe one lecture in class. I think a recorded video may not be ideal because I really want you guys to interact with me to see how that can be built. We're going to do one simplified Sudoku's puzzle solving in class together with you in TLA plus. You can bring your computer and do it. And then for one of your labs, we'll let you do another classic puzzle by using a model checker. You'll see some very interesting use of the TLA plus model checker. We'll do that. Okay? Anyway, just a look ahead. Okay? And for your information, for that Sudoku there, usually you might have to leave maybe about 10 to 12 different empty slots, right, in the Sudoku game. It turns out TLA plus cannot handle that state explosion problem. It turns out it can only handle up to 5 or 6 empty slots. That one there, think about, I'll just mention very quickly to you guys for your information. If I got 5 or 6, 1, 2, 3, 4, 5, 6, and each one of them can be filled out with 1 to 9. How many possibilities does TLA plus need to consider? 9 to the power of 6. And if you do the math, it's about 500,000 to consider. Somehow TLA plus couldn't really handle that. We tried that yesterday. But anyway, that's something for you guys to maybe try later. Yes, Chidalu. The number of combinations, the number of states you have to consider. Because to really consider what can be the possible value for each empty slot for Sudoku, there are 9 possible numbers you can fill out. So 9 to the power of 5 or 6. Yeah?
Just out of curiosity, would adding a more robust invariance make it so that way the state is more manageable as it tries to solve it?
Sorry, sit.
Because, like, for example, Sudoku, like, half of it is just So I feel like if you have stricter invariance, you'll be able to make it. You can make it like.
Yes. Yeah, there might be, yes, I agree. So there might be some optimization you can do from the model part. Maybe rather than brute forcing, trying literally just from 1 to 9, you might be a little bit smarter in choosing that. Yeah, well, we'll do that example in class. You guys can feel free to play with it and see if you can make it faster. No problem. Yes. Anyway, let's stay at the high level at this point. And you should know that this one is really about satisfying. By traversing the LTS, the graph of the state, of the model, of the system, you want to make sure this particular property will be satisfied. And you guys are very familiar with universal existential. We'll see some interesting temporal operators today after the little break. Okay, we'll definitely at least we'll see the syntax. All right, so that's about the summary. Oh, and this part here is decidable and algorithmic. Decidable because all we are doing in the model checker is just traversing a graph. So that's decidable. Depth first search, breadth first search, right? That's what you learned before. Usually depth first search, some modified version. And it's algorithmic. It's some algorithm that needs to be run by the tool. Yes?
I'm kind of confused why it's possible for the model checker to check everything, but it's not possible for an automated computer to check every single possible inference rule. Like, for example, the set of inference rules, why can't you just check every single possible one?
I think, I see what you mean. Because, yeah, it's, my intuitive answer would be, it's really hard to enumerate all the possible inference rule, right? Because sometimes you might need some special lemma to really prove this particular theorem. Or it's not really just about listing all the propositional theorem that we actually got in the textbook, and you can prove anything. Not really like that. You will need to prove any intermediate lemmas to really help some complicated theorem to be proved. So in that process, it's actually harder than if you try every possible system state that is derived from the LTS. Yeah, it's kind of different. I do see your intuition here, but they're quite different. Patrick?
Big difference that in the group-based systems you can go in infinite space. Like even if you have a finite number of rules of inference, right? Starting from one point you could go infinitely.
Yeah, you got lots of branches over there for sure. Yeah,
one branch is never guaranteed to terminate. It gets into the nature.
Yeah. I think that somehow once you branch to one particular part, yeah, it's the possibility just too many. Yeah. Yeah. Well, let's not go there. Yeah, that's yeah. But Chidaro, I like your intuition, but they're somehow different. Yeah.
How does the model checker know what to terminate?
Good question there. The model checker, yeah, I can tell you it really intends to terminate because when you try to build a graph, let's say the graph somehow can be built. But somehow when you try to check the formula, you want to traverse every possible state in the graph. Maybe while it is checking it, somehow the memory is already running out. In that case, we have to terminate it, right? That's really the only scenario you have to deal with, state explosion. Otherwise, you will definitely terminate. Basically, when you do depth first search in 2011, you got a cost stack for your depth first search. Finite. Exactly. Yes. All right. Good. All right. Yeah. Traversal of the state graph and shows that it is satisfied. Yeah. Exactly what we just tried to say. And then domain of application, hardware or software. I think for model checking, you can definitely do either. But we do more software in this course. And sequential or concurrent. Basically, sequential will be just one line after another. Concurrent will be something like a threading that you guys did maybe in 2031. We wouldn't do too much about concurrent in this course, maybe not. Okay? But reactive versus terminating. Reactive means the system should always be reacting to the stimuli from the external. Bridge controller definitely is one, because ML, MLN can keep happening as long as it's within the bound. Terminating is like an algorithm. Let's say if you do a binary search, it should terminate. Right? Pre-development versus post-development, yeah, either you try to do formal verification before you ever write your code, which is good, right? Or some people try to say, I have already implemented my Java code. I simply translate the whole thing into TLA plus and try to model check it. That's post-development. And we obviously know which one should be more preferred. But sometimes you may not have a choice. Maybe your company has never done formal verification before. Now it tells you this is our existing system. Now formally verify it. In that case, you cannot build from scratch. You got to translate certain part. In that case, give you a little bit tip. You cannot necessarily translate the whole thing into TLE plus or tool. You got to choose a critical part. Other part, maybe you got to do testing. Other part, you got to do theorem proving. So combination. All right, that's also background. Okay, we're getting very close to the LTL. Okay, for model checking, it will be for automatic and check-based, intended for reactive and concurrent, right? Here is just some very quick definition for reactivity, reactive system. Basically, gonna continuously run. Events should really keep happening. That's reactive, which we did in 3342. Concurrency means you just got interleaving operation from different processes, right? They just keep interleaving. They happen at the same time. And testing. I just want to show you guys one more thing. Did you guys take that software testing course before, right? Have you guys heard about a very famous quote by Dijkstra? Do you know who Dijkstra is? You know, the Dijkstra algorithm, that inventor. He said, testing, let me just show it to you. He said, program testing can only be used to show the presence of bugs, but never to show their absence. I think that one, the one implication is, that one reason is, usually when you actually do the testing, you got to watch out for the strategy, the quality of your test. You want to make sure the way you derive the test cases, they can cover different classes of input. Okay, different. If you miss any boundary cases, of course, it's not good enough. But model checking somehow makes sure you systematically explore all the possible system states for you. So it's not going to miss any cases. Right, model checking originally is only for post-development after the crisis occur. But now people also try to do before the developments. All right, very good. All right, are you guys ready for temporal logic? No? Okay, sorry, we gotta go there. I try to drag this as long as possible, but we're still gonna face it, right? Okay, how about this? Take a short break, and then we'll get there. Okay? Today will be relatively light. Take a 3 minutes break, don't go too far, and then we'll continue. Yes?
When
Yeah.
I saw that symbol, it's like with 1090 nodes.
Mm-hmm.
Is this kind of what the idea is? It's like we're essentially like we have a domain, which is our model, right?
Okay.
And we're essentially trying to prove a statement is true in the interpretation of the model, like in the context of
Yeah,
this
somehow the model actually satisfied, yeah.
Okay. So then when we say this, like the way that it was taught is like logically implies, like, but I guess it's the same as saying satisfies that condition, right?
It does. It seems to me this might be more like the like a V dash. You know,
Well, it's not necessarily like a V dash is like.
Oh, soundness completeness.
Yeah,
Yeah, that might be.
that's-
Yeah, you know what? That might be something I'm not. It's not included in my slide. That's something I can maybe also mention.
Like if you can prove the statement, then you can say that
There's actually. Oh, if you can prove it, that means it's really something that's correct.
Yeah.
Yeah, and completeness means if you're, the other way. Yeah.
in this book we talk about the model, right?
The model.
The model is like a combination of variables and
Constraints.
constraints. Right? So when we say like the model itself is a combination of statements essentially, right? So to prove the model, we have to prove that every one of those statements, like that.
The control
combination of
graph.
those statements
Yeah.
Can satisfy.
The property.
So it's the same idea.
Same idea, for sure. Yeah, I think it's a good point over here. Maybe at some point I can mention this too. That's also good for information. Yeah, I'll mention that too. Yeah, that's good. It's good stuff. Okay. Yeah, we're resuming in 2 minutes. Okay. All right, 1 more minute, and then we'll get started. Okay. All right, let's get started, okay? But don't worry, the first slide is a little bit text before we see some formula, okay? Well, for temporal logic, so this part over here about label transition system, we wouldn't touch it this time, okay? So guys, there's one thing important to clarify first, okay? Don't worry, pretend you didn't see it, okay? There's gonna be a count a little bit later. I don't want to scare you at first, okay? Just to give you guys a very quick roadmap. For today, and possibly part of next time, we're going to focus more on the syntax. So for temporal logic, okay, 2 aspects we need to cover. Number 1 will be about syntax. And after that, we're going to do semantics. Do you guys know about the difference between these two? Thomas? Yes, pretty much accurate. Syntax will be not just character. Character will be more like at a lexical level. It's more about structure, right? About the structure for the various thing you can write. Anyway, pretty close. So this will be the structure. Like what kind of operator can you use? Are they unary operator or are they binary operator? And what are the syntax, right? That's something we'll talk about today. Structure. Semantics will be, you're right, the meaning. And once you know about the meaning, you can kind of imagine how the model checker is going to check the property for you and how you can express the property. Okay? You want to know, number 1, how to express. And also, roughly how to check. We can get a little bit intuition. And also, number 3, when the check fails. How are you supposed to interpret the error trace? We talk about the strategies for proving or disproving universal and existential quantification. Also, for the temporal logic, you also need to know for each property or each operator we use, how do we prove it and how do we disprove it? That will also be about semantics, okay? Just to give you a look ahead. For today, mainly about syntax. And we'll do some interesting, not really interesting, but about tedious, but it's got to be done. Some foundational exercise about syntax. We'll get there. Okay, a model and abstract way. That one is just a repetition from before. Properties and temporal logic, okay, incorporates a notion about timing, okay? Basically, you can think about the timing here is not absolute. We're not talking about like 1 hour, 2 hour, or 3 hour, or like a 9:05 a.m. Not really. It's relative timing. Like one state may come later than the other. That's the timing, relative timing. And then, not statically true or false, meaning that it is no tautology, really, like something that will always evaluate to true. But rather, you just want to see how the system evolves by taking transition and then check it. That's what I meant. Verification. Yes, model checker. And that's exactly what we just said. It's going to be a decision problem by the model checker by exploring the LTS, label transition system, state graph. All right, so these are the 3. Let me just put it here. Okay, model checker. Think about the big picture, and then we can go on to see the syntax. Think about if this is your model checker. Model checker. Here we use TLA plus. But there are others as well. Just in case you guys are really intrigued, attracted to this area. There are also some very famous model checker. I'll mention a few. One is called spin model checker. Okay, another one is called WUPAL. Okay, just mention the name. In case you're interested, feel free to explore. But for this course, only TLA plus. Okay, and what does it take as input? Input is going to be the model. And I'll be a little bit more elaborate about our context. Another one will be the formula, phi. And in our case, think about the model here is some state graph. Based on TLA plus predicates. But you don't really write TLA plus predicate. Instead, you write something that can be automatically translated into TLA plus predicate. So let's make that note precisely. This guy over here is auto-translated from plus cal. From plus cal. Right? Just to clarify what the model is for this course. And the phi over here is basically the formula, right, in TLA plus also. That's really in TLA plus. That's something you got to write. Usually just Boolean. But we're going to learn about how you can do some temporal formula also in TLA plus. We'll do that in the later lab. All right, I'm running out of space. If you don't mind, I'm going to move it to over here. Oh, not very good, sorry. Yes, exactly. That's the beauty about using this. Oh, sorry. Sorry, bear with me, 10 seconds very quickly. I'll put it here. Over here. Over here. There we go. Make it a bit smaller. There we go. Okay, so 3 outcomes. Outcome number 1. Oh, sorry, let me do one more thing. This one can be moved to over here. Okay, 3 outcomes. Either the model checker will tell you, yes, the formula satisfied. That's true, all right? Or it might tell you that, no, it's not the case. Not the case. In that case, the very valuable thing about model checker is it will give error tricks. Okay. The third one, unknown. You don't really know whether it's true or false because somehow when model checker is trying to do that for you, it runs out of memory. State explosion, exactly. Thank you. State explosion. In that case, you have to type the top command in the remote lab and kill the process because it simply just freezes. Okay? Yes, Patrick, question.
It's like a fancy function, I guess, if you think about it, right? Like, give it some input and it'll give you yes, no, or either.
Yeah, sure, absolutely. Yeah. Alrighty, right? That's a very important picture for this course, right? Very important picture. All right, after this, LTL. All right, LTL, there we go. All right, LTL, linear time temporal logic. Okay, that's an acronym. It has, whenever we say connectives, actually that's what the textbook uses, but they really just meant operators. Don't be too scared by the term. They will allow us to really refer to the future. I might say this property here, it doesn't really need to be satisfied at the current state. It can be satisfied at some future states. How many states away? I don't care, as long as some future states. Okay? So that is why usually for LTL, it's really for reactive system. Because for your system trace, it can be infinitely long. Okay? So 2 features for LTL, and then we'll see the syntax. Something called computation path. Okay, it's just definition. What does that mean? So we try to model the time as an infinite sequence of states. That's one computation path. Okay, I'll show it to you. Very simple. Okay. So we talk about computation path, or just a path. Okay, you can ignore the computation if you want to. So think about, it's simply a sequence of states. Like a sequence over here. And etc. Okay, infinite sequence. Sequence of states that models the time, which always continues. And this is also why the model checking is very natural for reactive system. Okay, we'll go more. You can imagine that next Tuesday when we come back for the semantics for LTL, we're going to draw many diagrams like this and try to visualize the effects or meaning of each temporal operator. We'll get there. Yes? Oh, I got to clarify. The state graph itself is actually finite. You got to store that in the memory. But here we're talking about a trace, for example. I see what you mean. Yeah, I thought about some people might get confused. Very good. Think about this is state graph. For example, it might be if it contains a cycle, which is very possible for reactive system. Okay, somewhere over here, and then somehow it comes back, right? And etc. Right? With a cycle. In that case, this state graph itself is finite, but you can easily create infinitely long trace, right? By following cycle. I can go all the way to over here, and then go back here, and go again and again. That's infinite. Okay? Jora. Infinite trace. Yeah, let's be very clear. So think about the infinite sequence over here is about the trace. Okay? On the other hand, the state graph has to be finite. Otherwise, it cannot fit in, cannot be solved by the model checker. Must be finite. Actually, it should be small enough to fit into memory. To be fit to memory. Yeah, very good question. Definitely want to distinguish between finite states, finite state graph, but the sequence, like a trace, can be infinite. That's really important to note. All right, that's the first concept about computation path, the trace. And then undetermined future. This one here is kind of mentioned in the textbook. I will mention that it's a bit vague at this point, but let's go over that, but we'll see more clearly later. Basically, you want to think about there are multiple paths that might exist from the current states. And we just have to consider some of them that will actually happen to be the execution. But don't worry too much about this particular concept over here for now. I'll try to elaborate on that a little bit later. Right? This simply talks about we're going to consider alternative, possibilities for the path. All right, long promised, long waited syntax for LTL. Okay, for today, let's go over the syntax. Okay, very quick. We are able to summarize in one page about the syntax, and then we got several basic stuff to clarify today, and then we'll do some exercises. Okay. And also we need to understand the concept about grammar. I know you guys were not required to take 2001 to learn about context-free grammar. Don't worry. I think I'll just give you guys some very practical knowledge about how to manipulate it. We need that when you learn the new notion. Anything that's not clear, always ask me, but I'll try to give you just enough so you can understand. What we're trying to do is we say phi here is a temporal logic for LTL formula. And the way we define that is recursive. Okay, I'm going to switch to iPad to make many notes, but I want to show you at one go first. We say that a formula phi can be just true or false. So can think about these two are some base cases, true or false. Okay. And also, it can be some propositional atom, like a propositional term. Okay. Like whether this particular computer is free for use, or the printer is actually free. Okay, a proposition. And we got negation, we got conjunction, we got or, we got implication, and etc. Right? So these are still possible to write in the temporal logic formula. Still possible, right? We just got additional operators. And there we go. Okay, one operator is called the next operator. Okay, another one is called the future state operator, globally true operator. Also until, weak until, release. So these are all the temporal operators we have to learn gradually. Okay, we'll do example, don't worry, but we gotta learn them. All right, let me just go over a bit, give you a little bit more detail that you should really watch out for. Okay, you can think about this part over here, of course, is still propositional logic. This part here, you should feel very comfortable. Propositional logic. Okay, and I will talk about how you can really interpret over here. Let's say this. In order to define this, okay, let me say this. I'll give you one example here. Just start with some simple. If I say I have a phi over here, okay, and then this one over here, by definition, it could be maybe phi and 5, right? Okay. What I'm doing here is something called derivation, which I will try to give you some exercise about as well. Okay. And then here, you can think about these two are yet to be instantiated with some base cases. But here, I can say, for this left phi over here, I want to instantiate it by maybe some proposition, let's say, which will be P and phi. So this part here is still yet to be instantiated. In that case, I can choose to say I want to do this one here. P and X phi. All right? And then phi over here can also be instantiated in any way you like, let's say true. X, and then true. So this is a formula that's valid according to the syntax. Okay? Let me give you some terminology. We'll do exercise later. Okay? This is so-called a valid LTL formula. Derivable from the grammar. All right, it's not too bad, right? You're already learning some very practical theory about grammar. Okay, I'll just go very slowly. What you guys want to know is whenever you see phi, it's like calling itself, like a recursive definition. Okay, good. And a little bit more, all right? So, in the temporal, in the LTL operator, we got this category and this category. A simple thing to see at a syntactic level is like this. These are the so-called unary operators. And these ones over here, let me choose a little bit differently. How about this? These are the binary operators. Well, obviously, you can see for the unary one, this can only be one phi that goes after that. And for the binary, you got to get both, left and right, left and right. Okay? And very, very quickly about how you can understand. These three are the easiest one, relatively easier ones to understand. Well, maybe we'll start with them first. If I say x phi, that means I'm expecting the next states to actually hold this formula. Let's say, for example, if I'm currently here, I want the next one to hold this phi. That's what next means. Literally, from state I, I wanted to hold in state I minus I plus 1. Yes?
It's saying that we have to preserve truth in the next state.
In the next state, yeah, for that property.
Is it like a meta implication? Like if phi is true, then the next state phi must also be true?
No, it's not that. It's not like that. It's simply saying, let's say, for some, we're going to specify more clearly later. Let's say if somehow I'm here, that's my current state. Maybe satisfying, maybe P already. Here, I want to say next phi. That means this current state, I don't care if phi is satisfying or not. I just want the next state, literally, that one there, to satisfy. That's what it means. I'll be more precise next time, okay? Here, just want to give you some intuition. And this one here is also very useful. It's called a future states, and it's also called eventually, okay? That might be easier to understand. F over here is called eventually. Okay? Let's say I got some infinite trace over here. I want the phi to actually satisfy. If phi is not satisfied here, I'm not violating it. If phi is not satisfied here, I'm also not violating it. But I'm just saying at some point in the future, that phi must be satisfied. At some point. I don't care how far future it is, as long as at some point. Okay? That's the future operator is saying. And this one here is more like an invariance. It is saying globally, every state should really satisfy this. Okay? So these are the most commonly used. We're going to use it, but give you a little bit heads up. Okay? Later on, we have to distinguish between, over here, for example, of some very commonly used pattern. F, G, phi. G, F, phi. Okay? I'll help you a little bit over here. How do you analyze this pattern over here? First of all, it binds like this. So we consider G5 and F5 first. So I'm saying that at some point, this is satisfied. This is saying always the case, at some point this will satisfy. But it does make a difference. We'll talk about it too. Okay? You go, the way you associate, that's correct. Yes. Yes, question? Yeah, in some way, yes. Yeah, that's a very good, it's a very good observation. So the way we're going to define the semantics next time is by using some quantification over the trace. Yes, exactly. Very good. Absolutely. And any properties, for example, you want to prove about the temporal operations, you have to maybe go back to the predicate calculus to do some universal quantification proof based on the predicate logic. Right? So these three, I would say, don't worry too much for now. That'll be too complicated to explain intuitively. Don't worry, we'll get there. Okay? All you got to understand is these are unary and these are binary. Okay, good for now. And let's go over some very basic facts. We might just be able to do some exercises today. So the P here is one base case. You can do any proposition facts. Just give you some example. You might say printer LTR2 is available, right? You might say the reading of certain sensor for the nuclear power plant does not really exceed certain threshold. That's another proposition, right? Also, you can say maybe the Sudoku board somehow is filled with the correct solution. That's also one proposition. As long as there's no uncertainty here, it should be evaluated to either true or false. So that's a very definition for proposition. Yes?
Propositional adding is also a base case, right?
Yes, they are base case for sure. Yeah, if you go back here, very good. You can think about, we got only 3 base cases. And actually, so far, I was kind of expecting you guys might ask me one question. Give me a moment. Yes, you can think about these three. Yes, they are the base cases. Okay. I thought you guys might ask me, oh, aren't there some missing syntax over here? Did you guys? Oh, didn't you guys miss your best friends? We didn't have this. We didn't have that. In some, you're right, we don't need them. But what's the reason for that? I'm going to tell you, okay? So you might be wondering, why are we not having for all exist in the grammar over here? The reason is, very quickly, once we see the semantics, it will be clearer. In one of the slides, I actually told you that. Basically, to define these operators, somehow you have to use universal or existential quantification. So in some way, it's being there implicitly. So we don't really use it, okay? Because now the way we want to think about how things should be done is a little bit different from how we just do predicate logic, right? So these operators over here implicitly have some quantification, implicitly, okay? That's the final point I would like to make on this one here. Think about all these operators have some implicit. All these implicitly use for all or exist. That's why we don't really have that explicitly in the syntax. Okay. Okay. And then, yep, that's exactly the point. And whenever we got universal existential, remember we talk about universal disclosure. You might be wondering what they are. They are just path about the trace. Okay. That's something that'll get more and more clearly later. Okay, and let's talk about some precedence issue about how should we bind formula if we don't have any parentheses. So here are the principles that we're going to adopt. Number one, the temporal operator should really bind tighter than logical ones. For example, if you got something like this, I'll give you one example. So we talk about operator precedence. Okay, so operator precedence. So for example, let's say, let me choose maybe the future operator. Let's say, let me just say phi over here, right? Just for the sake of showing you syntax. Phi 1, phi 2. Okay? So now, how are you supposed to understand it? I can tell you there are two possible ways. Either it's like f with phi 1 implies phi 2. Number one, I'll say A here. Or it could be f of phi 1 itself implies phi 2. Right? Yes? Yeah, you may guess. Yeah, of course. That's something I wanted you guys to guess.
To me, A looks wrong. And the reason for that is because wouldn't the implication between two of these phi's like be a true or false value?
Absolutely. Absolutely. No. That's good. But remember, this one here is also some formula that's going to be evaluated on the state graph or the trace. This one here is going to give you true and false, true or false. Any formula you write based on this grammar can be checked by some model checker with either true or false or unknown. Any formula based on this. Okay, so both are valid.
But what does like the meaning of the future of one of the base cases mean? Like,
Okay.
does future of true or future of false have like?
So very quickly, yeah, sure. Yeah. So for this one here, the meaning would be at some point in the future, this implication holds true. This one here is saying that if at some point in the future phi 1 holds true, that implies phi 2 holds true in the current state. They are different. Okay? But we'll get there. Don't worry. So guys, the question is still unanswered. If I didn't really bracket this, does it really mean A or B? Based on the principle I just told you guys. Temporal operators should bind tighter than logical ones. Yes, A or B? Thomas? Exactly. Very good, very good. B should be the one. So that means you got to be very careful. If you're doing your lab, or in more general, if you're using the verification tool, if you really meant A, in that case, you cannot write just like this without any parentheses. You have to use parentheses to really enforce the order of evaluation. Okay? Chidalu, are you okay, or you're lost? Okay, sounds good to me. Okay. All right, so this one here. This one here is not what Formula 1 over here means. Okay? It's really important. Yeah, go ahead. Absolutely, because the principle is the temporal operator has higher precedence than logical ones. Yes. Yeah, I can put an order list for you. So precedence, let's put that first. So for precedence, think about from highest to lowest. There's a second principle before I give you the list. The second principle is, what about for all the temporal operators, are there any precedence? There is. You got to distinguish between unary and binary. Unary binds tighter than binary. That's a principle. Oh, that's also on the slides. So based on this, I can now tell you the precedence. Let's do that. Okay? I'll give that to you. Okay, the precedence, and then we can look at other example. Okay, precedence. So we got to go for the highest one will be unary temporal operator. X, F, G. If you really want to force a particular way to evaluate it, you got to use parentheses. They are the same precedence level. And then, so this is unary. LTL operator. The next one will be binary. UWR. U, W, and R. So these are the binary LTL operator. All right, so that's about the temporal operators, and then we got logical operator, which we know, right? And then we got logical. In that case, of course, if I remember correctly, so that should be N will be the negation, and then conjunction, and then disjunction, and then implication, and then equivalence. We don't really use that. I'll just include it. Yeah, but let me get rid of it. You don't really use that. It's not in the grammar. Yeah. Chidalu. Not negation. Absolutely. But of course, in TLA plus, it's the tilde, right? Just for your information. Yeah. Mm-hmm. All right, precedence. And we ought to do some example together, right? About 10 minutes, I can let you guys go earlier today, right? I think I already scared you guys enough about temporal logic, right? Haven't even talked about the meaning yet. Yes, go ahead. Yes.
Phi is just like x, right? So f of phi would be like something of x.
Okay, yeah. Okay, when I write, I write phi 1 and phi, are you talking about these two phis? Okay, phi in general. Okay, it's a symbol, right? You know, mathematicians or computer scientists, they like to use symbol to somehow denote something that is a placeholder. Okay, so here when I say phi 1 and phi 2, I mean any arbitrary formula that you can have. And here, the grammar is even the case. The phi over here, think about it's like a defining some function recursively. The phi here can either be as simple as these three base cases, or it can be as complicated as you like by deriving that using something I did over here. We'll do more exercises over here. So this grammar here can generate an infinitely many possible formula you might have. You got to choose the one that's valid and something you really want to express. Okay? Good. Yes, question? Where? Proposition, atom? Over here? Oh, yeah, good. So here is also one term that the textbook uses. Okay? think about atom over here, really like atomic description. Atomic in the sense that, of course, you wouldn't say, atomic description wouldn't be, I say, P is true and Q is true. It's not atomic because it contains two things that should be conjoined together. Atomic is something simplest possible but cannot be simpler. Right? It's kind of borrowing the analogy from physics. Atom is really the smallest. And here we're saying atomic statement means it's the simplest statement you can have. Which itself does not contain any operators. Any operators. Okay, good. All right, so that's about what we said. Okay, so here, this is something we got to do on Tuesday to finish the syntactical practice before go on to semantics. You really want to have a very good feel about how to write formula. What we're going to do is we're going to talk about parse tree. Okay, draw some tree structure to show the formula, especially when you're given maybe formula. I'll give you one example. All right, I did it randomly. Okay, but they're valid formula. Okay, so we're going to talk about on Tuesday. 1, 2, 3, 4. They look almost the same, right? But they all mean something very different. Not just the semantic level, but also in the syntactic level. How do we tell? We're going to show to you how to do parse tree and how to do something called leftmost derivation and what's called rightmost derivation. I'll do example together with you. They are not hard. You just need to know how to do it. Patrick, question?
Well, we're still talking about syntax.
Uh-huh.
On, I guess, the only written test we have is the final exam. But do you have a preference as to how explicit you are with parentheses? Like, I know some professors say don't use parentheses if you don't absolutely need them.
No, I wouldn't be that harsh. I would say I don't mind if you try to use parentheses over excessively, but I would rather that the order of evaluation has no ambiguity, right? For example, let's say if you really put something without any parentheses, you better mean what you really wrote. Yes.
If you want to be extra safe, there's no problem with
No problem.
writing in parentheses and saying it has to be right.
Yes, that's okay. Yes. We'd rather the meaning is actually right. Guys, how about one more thing, and then I'll let you go. Okay? One more thing that also, we'll do this exercise together on Tuesday. One more thing here. Okay. This. I'll talk about this quickly. So this one here is just about for the operators. Okay. Here, X, F, and G. Okay. Very quickly, just a few minutes. So we got X, F, and G. So these are the temporal operator, the unary ones. And in the textbook, they actually use the letter. So that means you're going to say X and then 5. Or you want to say X and then maybe P implies Q, right? For example, that's what you got to write, right? F and G and etc. You might see other literature, either the sometimes, mostly some article or some textbook. They also use symbols, okay? I'm going to show to you the symbol. You should know both. In the exam, I don't care which one you use, unless we got very strict rule to say you got to use symbol. Okay? You might like the symbol more, actually. Okay? I'll show to you very quickly, and I'll take question. Okay, for X, it will be a circle. Just a circle. For F, it will be a square. Want to take, for G is a circle. Beg your pardon. You want to take a guess what F is? Future. Triangle? Huh? Diamond. Aha, that's a good guess. Okay, anyway. Not too sure why, but it happened to be the case. All right? Diamond. That means this guy over here really is the same as circle this. Okay? And also, if you say FG5 is really equivalent to this, 5. They are the same. That's my point. So maybe it would be worth for you guys to get familiar with the syntax, and then before we talk about semantics. Oh, many questions. Okay, I'll take one at a time. Go ahead.
F corresponds to diamond.
Yeah.
Yeah, box followed by diamond, yes. FG, oh, yeah. You guys really pay attention to what I write. Thank you. Absolutely. Absolutely. Thank you. Thank you. Okay, Patrick.
Is the standard on the online tests going to be letters? Because I'm not typing this.
Yes, exactly. I'll be So if you're supposed to type something, you can always type letter, okay. On the exam paper, unless it say very explicitly what you should use, otherwise either one is fine.
But, generally, like, the letters are more convenient.
Yeah, I personally like the symbols, Yeah.
I guess I like the letters, how you kind of put in the word, and
Uh-huh.
it fits in, right? That's
Yeah.
where the letter comes from.
Yeah.
Next,
Oh, yeah, exactly.
future state, global.
Yeah, I'll leave the choice to you. Guys, thank you so much. You're dismissed. All right. I'll see you next Tuesday.